Today we're talking about solving linear inequalities and absolute value inequalities. So those are the two main topics for today, but we're starting off with a few properties. Just for your information, we have the transitive property of inequality and the addition property of inequality. Much like you've seen in the past, the transitive property of equality or the transitive property of congruency, it shows up here as well. So if A is less than B and B is less than C, then the transitive property says that A compared to C, A has to be smaller, A is less than C. And there's some numbers to give you an example. If 1 is less than 2 and 2 is less than 3, well, it makes sense that A is less than, or 1 is less than 3. Here with the addition property, we are adding the two smaller numbers. So we're taking the smaller number of the first pair and the smaller number of the second pair, we're adding them together. And then we're adding the larger number of each pair, and we're saying, hey, when you add up the two small numbers, it is still less than the sum of the two larger values. With the addition of a constant, this is the one where we're adding the same value to both sides. It preserves the inequality. So all of these have the same symbols with the if part and the then part of the statement. So we say that preserves the inequality. Now when we get down to the multiplication of a constant, we have two cases because either the value that we're using to multiply with is either positive or it's negative. So if it's positive, it preserves the inequality. It keeps the symbol the same. This is the one where it's different. If C is negative, then it changes the direction of the inequality. And as an example, if you have 1 times negative 3, that will be bigger than 2 times negative 3, because if you think of your number line, negative 3 is closer to the right-hand side of the graph. That makes it a bigger value. And number 6 is closer to the left-hand side of the graph, so that makes it a smaller value. So all of these symbols here have remained the same. So here we say it preserves the inequality. And so that means that you don't change the direction of the symbol, right? But when you get down to the multiplication of a negative, that also includes dividing with a negative, that's when it changes. All right, so that's sort of little topic number 1. Here now in the example number 1 with these 3 problems, this is a review of what we've done before in our review unit at the beginning of the year. We're using interval notation to write our answers here, so we're reviewing that. And all of these are just linear inequalities. You can see the power on x is just 1. So when we have a linear inequality, we isolate the variable as normal and rewrite our answer in interval notation. And in a couple of steps, we've isolated our variable. We get x is greater than or equal to 5/3. So if I were to draw a number line just to kind of illustrate what we have here, the number line goes from negative to positive infinity, and somewhere on that you have a value of 5/3. We want to shade greater than, so we're shading to the right of 5/3, but at the greater than or equal to sign, we don't use a dot, we're using this bracket. And the reason for that is because we want to bundle up these two symbols to use as our interval notation. So square bracket on the 5/3 includes 5/3 as a point that is a solution to this inequality, all the way up to positive infinity with a rounded bracket on infinity. So that's the interval notation. Here in part B, let's go ahead and bring the 2x to the right-hand side. Add 7 to both sides. We end up with 12 is greater than 2x. We divide away the 2, so we have 6 is greater than x. But in terms of formatting this, we want it to have the x on the left-hand side. So x is less than 6 is what we're looking at here. So as we set up our number line from negative to positive infinity, here's my value of 6. We're shading less than that, so to the left. That means we want these two values, the negative infinity and the 6, in the interval notation. Here we're using a rounded bracket on the 6 because it's only a less than sign. It does not have the less than or equal to, like what we saw here. If you have the equal to part, then you use a square bracket. Here's our last example in the series. This is a compound inequality, as we have now 2 of those symbols. Let's start by eliminating that fraction. I'm going to multiply everything by 2. That means we multiply the left side by 2, the middle by 2, and the right side by 2. In the middle, 2 over 2 cancels out. So we now have a negative 4 less than or equal 3x plus 1 less than 10. We're going to move the constant term away from the middle, so we're subtracting 1 everywhere, on the left, on the right, and in the middle as well. So we have a negative 5 less than or equal to negative 3x, which in turn is less than 9. Lastly, we're dividing away the negative 3, and because that's a division with a negative, we have to change the direction of our inequality. So we have a positive 5/3 now greater than or equal to x, which in turn is greater than negative 3. And again, we have to switch the statement around because we want to order the numbers from smallest to biggest. So negative 3 on the left and positive 5/3 on the right with x in the middle. So as you flip the statement around, the direction of the signs are also the mirror image. So here you can see this sign is the greater than sign. It points to negative 3. So now it's the less than sign. Again, it should still point to negative 3. So that's what it looks like. So we have our solution interval of negative 3 up to and including 5/3. So that's a review. That's our topic number 2. We're going to spend most of our time now on topic number 3, which is solving absolute value inequalities. Some of this you've seen before in your Algebra 2 class, and so some of it will be a review, but we're going a little bit further as well as we talk about this topic. So when we talk about the definition of absolute value, this is the official definition. It is the distance from 0. So if we were to take a look at setting up a scale here, I'm going by ones. If we were to talk about the distance from 0, and we'll use this as an illustration, if x, absolute value of x is less than 5, what it means is that this is a distance from 0. So 5 units from 0 takes us here at positive 5, and then also here at negative 5. So that's why we end up with 2 critical values, because it is a V-shaped graph that looks kind of like that. That will go right through the negative 5 and the positive 5. So at 0 we have our line of symmetry. At the bottom of the graph is what we call the vertex, so V for vertex. And the sides would go something like that. And so where the absolute value crosses the x-axis, those are the x-intercepts, and those x-intercepts are equally distant on either side of the vertex. Now here the vertex is 0. But we could take the whole graph and shift it to the right or shift it to the left. Then a vertex is not at 0 anymore. So we're counting the distance from this line of symmetry to that x-intercept. And this number is a positive 5. It's a positive 5 because it's a distance, but where you end up on the scale is you end up at negative 5 and at a positive 5. So it's because of this negative value and this positive value that when we are solving these absolute value inequalities, if we have the greater than sign, we have to pull that inequality apart and create 2 little mini inequalities to solve. Notice that we have less than the opposite of the number, so that negative c is this negative value on this side, and the x greater than c is the positive value that you see on the right-hand side. And we have to pull it apart into 2 separate little mini inequalities because we have to figure out the value on the left-hand side and then the value on the right-hand side. And we'll talk more about that in just a moment with the greater than sign. If you have the less than sign, once again, notice we have a negative value and a positive value. So there's the negative value on the left-hand side, there's the positive on the right-hand side. But here, because both of these are set up as a compound inequality with less than signs, we're talking about the interval between those numbers, we can just use one compound inequality instead of 2 separate ones, because the 2 separate ones are just talking about what's happening on the far left-hand side or the far right-hand side. So we'll look at a couple examples about this, which happens to be on the next page, but this is the template. This is what we'll come back and identify here in just a moment. So turning the page over, we're looking at a first example for the absolute value type problems. And it's set up a little bit differently. These are the examples that we'll be doing with the greater than sign and the less than sign. But to kind of put it in a greater context, we want to compare it to what we've done previously. What's the difference when you have an absolute value with an equal sign versus when you have an absolute value with a greater than or less than sign. They each mean slightly different things. And so we'll be referring to this picture quite a bit. I'm going to be color coding this slightly with a couple different colors just because there's a lot of information we're trying to pack into this one example. So let's start off with what we know how to do. Part A. We know how to solve this. We've seen before. The very first thing you have to do is isolate the absolute value, right? So we're adding 5 to both sides. Once that absolute value is isolated, then we split this up. We take that expression out of the grouping symbols and we say either x minus 3 equals the opposite of 5 or x minus 3 equals 5 itself, right? So again, there you see it. There's your positive and negative versions of that 5, just like what we'll be doing here in Part B. So adding 3 to both sides, we get negative 2 and 8. And we've learned in the past that these numbers are the x-intercepts, and that's why we can interpret this as, when you see the equal sign, the solutions are telling us where the absolute value is on the x-axis, and that's where it's intersecting the x-axis. We call those x-intercepts, but in this section, we're also going to be referring to them as critical values. A key part of the work that we're going to be doing is first finding the critical values, and this is how we can do that. So what that means for us, I'll use a scale of 2. Is that we have a critical value at negative 2 and positive 8. So that means we know the V-shaped graph will go through those values right there. Those are the x-intercepts. Now, we also know that because this V-shaped graph is going to be symmetrical about the vertex, we want to figure out where's that line of symmetry. Where does it show up? Well, it should be right in the middle, smack dab in the middle. So if we count the total distance from end to end, 2, 4, 6, 8, 10. 10 is the total length. We want to put that line of symmetry right in the middle so it'll be equidistant from either side. So 10 divided by 2 is 5. We want it to be 5 units from either side. So 1, 2, 3, 4, 5. So this is the line of symmetry. And again, we should be able to count 5 on the other side as well. 1, 2, 3, 4, 5. Somewhere on this is the vertex. And so this is our absolute value graph on the number line. So this is the vertex, and we usually refer to that as H and K. And this distance right here, that's the 5. So notice that 5 of distance is showing up right here. That's the number that we see. There it is. We called that the letter C on the previous page. So that letter C is the distance. We've seen that here before. That value that we're calling C, that is the distance from the vertex to the critical value, the x-intercept. So when we have the greater than sign, again, we have to isolate the absolute value. So we have absolute value of x minus 3 is greater than 5. And we saw from the previous page that, again, we're going to split this up into 2 different little mini inequalities. So we have x minus 3. Now you change the sign to less than, and you make it the opposite of 5. So you change the direction of the sign, and you change the sign on the number. Or we have x minus 3 is greater than 5, just as you read it right there. So we're adding 3 to both sides, so you get x is less than negative 2, and x is greater than 8. Notice you get the exact same critical values. So those numbers show up the same way. But the inequality is now meaning something different, because when you have the equation, that tells us where the graph is on the x-axis, which are the x-intercepts. But now, with this greater than sign that we had in the original problem, we're talking about where's my graph above the x-axis. Right, so I'm going to color code this a little bit, using the orange color here to shade in the regions where we have the graph above the x-axis. You can see there are 2 regions. That means there are 2 solution intervals. So we want to talk about this solution interval, which goes from negative infinity up to negative 2, and this solution interval, which goes from positive 8 up to positive infinity. So if we write our answer, we will say negative infinity to negative 2 in union with 8 to infinity. So that symbol right there, we say the union symbol. It means even though there's that gap between the numbers of negative 2 and positive 8, we're sort of combining. It's both of these at the same time that make the entire solution. It's not one or the other, it's both of them at the same time. So then if we have the less than sign, all right, so I'll color code that. We're talking about where's the graph underneath the x-axis. You can see that's right here, and that gives us one interval. That means we should have an answer that is only one interval instead of the two intervals that we saw previously. So if we only have one interval, that means we have to set up the problem in such a way that it will only give us one interval. And again, going back to the template on the previous page, this is the one interval. Notice previously we had two intervals because we had two separate little mini inequalities, but this is one giant inequality, and so that means it's one interval. We still have the negative value and the positive value on the outer sides. So step number one is always isolate the absolute value. So we're adding 3 to both sides, so it's less than 5. Then we're going to take this out of the grouping symbols, but we only need one copy of it this time, and we surround it with the less than signs. We have the negative 5 on the far left and the positive 5 on the far right. And then when we add 3, we're adding it to the left-hand side and to the right-hand side, as well as to the middle there as well. So we have negative 2 less than x, which in turn is less than 2. That should be a positive 3 as we're adding 3 to both sides. So negative 2 less than x less than 8. Notice we get the exact same numbers again, so we still have those critical values. So in other words, those critical values are taking the entire graph and they're segmenting it. They're chunking it up. So you've got this interval on the left, this interval in the middle, and this interval on the right of the critical values. So the interval notation itself for this part C is negative 2 to 8. Notice we have one interval because there's only one space under the x-axis where the absolute value exists. So when you see the less than sign, think of it as sinking down under the x-axis. And when you see the greater than signs, thinking of it as rising up or going up and above. And when you're above the x-axis, you have two intervals, and that's how you know you should have two interval answers, joined with the union sign. We're going to be building on this concept in the days to come in the following notes. We'll be talking about above and below the x-axis, and we'll continue with that in a moment. But building on these two examples here, we're doing this kind of work again right here in example 2. So once again, we're going to solve the absolute value inequality, and we want to use interval notation. Here in part A, this absolute value is already isolated, so we don't have to move anything around right now. I observe the sign. It's a less than sign, so that means it's under the x-axis. That means I would expect to have one interval as an answer. And the only way to set up one interval is when you have the expression surrounded by those less than signs with a negative 7 on the far left and a positive 7 on the far right. Let's start by multiplying everything by 2. So in the middle, 2 cancels out with divided by 2. We have a negative 14 less than x plus 4, which in turn is less than 14. Next, let's subtract 4. So we should have a result of negative 18 on the far left, less than x, less than 10. So there's our one interval from negative 18 to positive 10. If we were to represent that on the number line, here's my negative 18. I'm not really putting a scale on that, just for space, because otherwise it'll flow across the page. But it will look like this. That's how we represent that one interval. But what it's communicating is that you have this V-shaped graph that goes through those critical values, and we're asking where's the graph underneath the x-axis? It's underneath the x-axis between the values of negative 18 and positive 10. So here in part B, we have a greater than or equal to sign, and so when I see the greater than sign, that tells me I need two intervals, because the only way we find intervals above the x-axis will be on the far left-hand side and the far right-hand side. So that means we need to set up this problem as two separate little mini problems to solve. First, let's isolate the absolute value by dividing away the 3. Now we can separate this, so we have a 2 minus x. Here we change the sign, and we change the sign. So you change the direction of the sign, and you change the sign on the value itself. And the 2 minus x greater than or equal to positive 2. So I'm going to subtract 2 from both sides. We get a negative x less than or equal to negative 4. Dividing away a negative 1, we get a positive x. Change the sign again, as we're dividing by a negative number. X is greater than or equal to positive 4. On the right, again, subtract 2 from both sides. We have a negative x greater than or equal to 0. Divide by a negative 1. And again, change the direction of a sign. So we have now two intervals. We can fit these numbers a little bit easier on this number line. So here I will create a scale going up by ones. And so we're saying that x is less than, so we'll shade to the left of 0. So that's going to be like so, to negative infinity. X is greater than 4, so we'll shade to the right of 4 up to positive infinity. And so that's what my number line looks like. We've shaded to the right, we've shaded to the left. So my solution interval is from negative infinity up to and including 0 in union with 4 up to positive infinity. And what that is representing is right in the middle, there's my line of symmetry. Here's my absolute value graph. And when we have the greater than sign, we're saying, where is the graph above the x-axis? And so here you can see that when we're saying from negative infinity up to 0, we're saying that's the region, that's the interval where the graph is above the x-axis, and then also on this side from positive 4 to positive infinity, that's where we find the graph above the x-axis. So now what we're going to do is we're going to go backwards. In the next set of examples, we're going to start off with the solution interval and see if we can work our way backwards to figure out what was the original problem. Right? We're going to give you a solution interval. We have to work our way backwards to figure out what is that problem. So in writing this, we need to know some key ideas. We need to know, is it a less than sign or is it a greater than sign? Do we have this value here identified? Again, we said this value on the right-hand side, like we saw up here. That value on the right-hand side is the distance from that line of symmetry to the critical value. So we want to know what that number is in building our inequality. We also want to know what is this number here on the inside. And so that's represented in a more abstract case down here in this box. And then we'll look at the examples on the next page. So where it says, if pointing in opposite directions, what we're talking about is if you're pointing, I have an interval to the left and I have an interval to the right. Kind of like what you see here. So if I have negative infinity up to some number, we'll just use a as a placeholder, in union with b to positive infinity. What that means is you see a number line that looks like this. You're pointing in opposite directions. So something like this. Right, so if that's what you see, that means we have two intervals. And if we have two intervals, that's representing where the graph is above the x-axis, and that's how we know to pick the greater than sign. However, if we're pointing towards each other, meaning you have something kind of like the example up here in part A, right, these are pointing towards each other. This is only one interval. Where do we encounter a solution that only has one interval? Well, that's when we're underneath the x-axis, and that's how we select the less than sign. So if you have two intervals, select the greater than sign because you're above the x-axis and there's two intervals above. If you have one interval, you select the less than sign because there's only one interval underneath the x-axis. Additionally, we said that right here's the line of symmetry, right in the middle. And that number is going to be found from the letter H. So if we can figure out where is that vertex right there is at H, comma, K. And there's the H. So if we can figure out what the H is, it goes right there in the template. So we're not focusing on the K because we're not plotting points on an XY grid. We're just representing them in one dimension only, just the horizontal number line. So we only need to know the horizontal value. We don't really need to know the vertical value for writing this equation. And then we said that letter C is going to be the distance from the vertex to that x-intercept, and you can count it in either direction. So those are the three pieces of information that we need. We need to know what is the vertex's location with the H. We need to know this distance, and we need to know whether we pick the greater than sign or the less than sign. So to find the H, this is going to be the halfway between the endpoints. In other words, find the average. So we'll be doing that in a moment. And then to find the C, we can just count the number of spaces from the H to the endpoint. And that'll do it. So let's go to our two examples. I'm going to the next page. And we've got them here at the top. All right, so what we're really given is we're given the solution. This is the solution interval. So the solution interval in part A is going from 4 to 8. And what we really want to do here is we want to write the absolute value inequality. So that means we have to have absolute value signs, and we have to pick whether it's a less than or a greater than sign. So let's use a picture to help us figure out the information we need. So 4 and 8 are critical values. I'm going up by ones on my scale. And putting a point at 4 and at 8. So those are the x-intercepts. So that tells me that my absolute value is going to go through those 2 points. I might have the vertex in the wrong spot, but I'll adjust that slightly. I'm just kind of, I'm estimating that's what it should look like. So to find the value of H, that's this guy right here. We want to know where is that vertex at. That's going to be smack dab in the middle between 4 and 8. So we can find the average. So 4 plus 8 over 2 is finding the average. And that gives us a result of 6. So we know that 6 is where that line of symmetry should be. So right here, so my sketch is slightly off. That's what we want right there. And once we have that number, now we can just count the distance, and that'll create the value of C that we need, and in this case, it's 2. So we just count 6, 7, 8. From 6 to 8 is 2 spaces. The next thing we have to do is we have to pick, do we want the less than sign or the greater than sign, right? Which one do we want? So we are provided one solution interval. And so the question is, where do we find one solution interval? Is that found above or below the x-axis? That's found below. So because it's below, that means we want the less than sign. So the template is absolute value of x minus h, and then one of those symbols, the less than symbol, the letter C. So we have x minus 6 in the absolute values, less than 2, and there's the final answer. So if we started with this and we solved for x, it would take us back to those critical values and that solution interval from 4 to 8. So here's the last one. Here we have now 2 intervals. There are your critical values of -6 and +2. So again, let's create a little picture here. I'm going by ones on my scale. So we have a critical value at -6 and at +2. So let's find the vertex. H is going to be the average. So we're going to take the -6, add it with the 2, and average it out. So that gives us a placement of -2. So there's my line of symmetry. Somewhere on that is the vertex. So that vertex is located at -2, comma, some value of k that we don't need for this process here. Next, we're going to count the distance. This will be the letter C. So let's see, 1, 2, 3, 4 is what we want. So C is 4. And then we have to determine, do we want the less than or do we want the greater than sign? So we look to see what is my solution interval. There are two intervals, so we ask the question, would I find two intervals both above or both below the x-axis? And we find them here, above. So above means greater than. So the template that we're using over here, absolute value of x minus, the h is a negative 2. That'll be greater than the value of c, which is 4. So just to clean that up, absolute value of x plus 2 greater than 4.